When we looked at the scalar or dot product in component form, we've seen that it could be written like this. Vector A dot product with vector B is A1 B1 plus A2 B2 plus A3 B3. So what we do is we multiply the components of each of the vectors out, and this gives us our dot product. And I mentioned in the video that it's not wholly obvious that that should be the case. So let's have a little proof of that, and it's a little algebraic proof. Now, I never introduced this proof at the actual time whenever we were learning about the dot product, because this proof needs you to understand a little bit about vectors, and we hadn't covered vectors at that point, so that's why I had decided to miss that out. So let's talk about this now. Let's say, for example, we take the vector A and we can write it in component form. We can write it, in terms of the vector. So we could say vector A is going to be the A1 in the I direction plus A2 in the j direction plus A3 in the k direction. So remember, whenever you did your vectors, we're just going to have your three-dimensional space. We could say x is in this direction, y is that direction, and z is in this direction. And the x will have a component vector I, which is of length 1. And the y will have component vector j, which is of length 1. And z will have a component vector k, again, which is length 1. And we can denote a particular vector there as a multiple of each of these. So this vector here is going to be a certain distance in the x direction, so it would be A1 in the I direction, say this point here, and then it would be A2 in the j direction, and then it would be A3 in the k direction, and this would give us our vector. So you've seen that whenever you did the vector section. So we're going to have two of these vectors. So we're going to have our vector A and we're going to have our vector B. Now we noted also that whenever we took the dot product of these component vectors, we had that I dot I equals j dot j equals k dot k equals 1. And again, this was just a geometric thing. We said that the dot product in words says what component of this vector is in the direction of this vector here. So in the case here of the I, j and k, if we were to draw these out, there's I, j and k. So we're going to again have our z, our x, and we're going to have, let's say that's our y. Then this would be the I component. And this dot product here, I dot I, would be saying how much of I is in the direction of I? Well, the length of I is 1. So how much of an I is in the direction of I? Well, how much is the value of 1? Okay. And the same for the j dot j. We're saying how much of the vector j is in the direction of this vector j, and it's 1, and the z and the z. So that's going to give us a value of 1. Now equally, when we look at the I dot j, j dot k, or k dot I, then these are going to give us a value of 0. Because this one here, for example, says how much of the vector I is in the direction of the j, and that's going to be exactly 0. Because in this instance here, if this is I and this is j, then there's no component of I in the vector in the direction of j. It's just like having your 90 degrees, and we're having a value, let's say j is there, and let's say I is there. There's no component of I in this direction. It's all in that direction. There's no component of j in this direction. It's all in that direction. So it means then that the value of this here is equal to 0. So again, we've seen that whenever we looked at the vector section. And if you haven't looked at the vector section, obviously you'd have to have a little look at that before this proof means anything to you. So we've got these two here. Now let's say, for example, we were to just multiply these two vectors together component by component. So really what we're saying is we're going to have A1 in the I, A2 in the j, A3 in the k, and we're going to multiply these three together with these three. So again, we just use the normal multiplication. We're going to have A1 in the I direction times each of these three, so that's going to give us the first three components. We're going to have A2 in the j direction times each of these three, so that's going to give us another three components. And finally we're going to have A3 in the k direction times all of these three, and that's going to give us a final three components. So we're going to end up with 1, 2, 3, 4, 5, 6, 7, 8, 9 components. But you can see that whenever we multiply these components together, the first one here, for example, is going to have it's going to be A1 B1, and it's going to be I times I. So that's what we've got here, A1 B1 I times I. And the next one would be A1 B2 I times j, A1 B2 I times j. And finally for this one here, it would be A1 B3 I times k. That's A1 B3 I times k. Now you can do the same for this one, multiplying the next three, and this one multiplying the next three, and you'll get all of these components. But a thing to notice here is that we're going to use these identities here to simplify this, because we know that I times I is equal to a value of 1. So this is a value of this I times I would give you a value of 1. So I'll just pop it above there. So that's going to give us a value of 1. The I times j, well, that's going to be 0. So this term here will cancel out. And again, the I times k will cancel out. I times j is going to cancel out. The j times j will give you a value of 1. This is going to cancel out because it's jk. Ik cancels out. The jk cancel out. And the kk gives us a value of 1. So it means that these ones with the crosses, they're all equal to 0 because we've got the 0 here. So that's equal to 0, that's equal to 0, 0, 0, 0, and 0. So we're only left with three terms. We're only left with this term here, the A1B1, the A2B2, and the A3B3. And this here is nothing other than what we had above, which is the dot product. So the scalar product in component form is going to be given by the A1B1 times A2B2 times A3B3. Now that's like an algebraic derivation of this. So that's all for this video. Thank you for listening. I'll get you in the next video. Goodbye.